Hey everyone, so this is the next lesson where we're going to be continuing our discussion on how to do log equations. This time we're going to talk about logs on both sides. So before we continue, let's start working on some of these questions. So first thing that we want to do, we want to solve this for x. So first we want to just kind of isolate the term that has x. So we're going to add the 5 to the other side. Now, there's a few ways I could go about doing this. I could do logs, I could do some other things, but the easiest thing to do, since I know 9 can be rewritten as a power of 3, I'm going to try to go through the common basis, turn this into 3 squared. And from here, I'm going to just set the exponents equal to each other. So 2x plus 1 equals 2. Subtract the 1 over. 2x equals 1. And we get x equals 1/2. All right, over here. Here I need to try to get rid of the log term. So the x that's a base here gets moved over here to the other side. So it becomes 6 equals x to the 1/3. I can move the exponent over to the other side by just doing the reciprocal. So instead of x to the 1/3, I can write it as 6 to the 3/1, which is just 6 to the 3rd. Plug into the calculator, and we get 6 to the 3rd equals 260. All right, so just as a refresher, we have names for special log terms, like log base 10 is called common log, since it's the most common one that you'll see. So for example, log 8 has a base of 10. If they don't say what the base is, it's assumed to be 10. If we have a log term that's base e, we call this a natural log. And here ln e has a base of using the calculator, we could say that e is equal to 2.7183, and that ln of e is equal to 1. All right. So the way we're going to go about doing these solving log equations where we have logs on both sides is pretty much similar to the whole common basis. What we're going to do is just set what's inside equal to each other. So you're going to be using your entire rules of log terms in order to actually do this. So you're going to do the whole condensing using the multiplication rule, the quotient rule, the power rule, so that you get one log term on the left and one log term on the right and nothing else. Once we do that, we can just set the exponents, sorry, not the exponents, but the insides equal to each other. Subtract the 2k, add the 5. So this becomes 2k equals 4. Divide both sides by 2, and we get k equals 2. And then we could so they want us to actually verify. So before I move on, 4 times 2 minus 5, that's can be rewritten as log of 8 minus 5 or log 3. They say that this is going to be equal to log 2 times 2 minus 1. So the right hand side now. So log 2 times 2 is 4. 4 minus 1 is log 3. So I get log 3 equals log 3, which makes sense. All right, so some of these practice problems. And remember, the only way that we can actually do these is if the log bases are the same. So here, both these log terms are base 12. And the thing is, it doesn't even actually matter at this point, because all we're going to do is set the insides equal to each other. Move the 12b plus 1, add 12b plus 1. And we get b squared plus 12b plus 36 equals 0. From here, we're just going to factor. So this is b plus 6, b plus 6. Since 6 times 6 is 36, and 6 plus 6 is 12. So this tells me that v is going to be negative 6. I'm sure if we plug it into the equation, we will get the, this is my answer. All right. So for this one, do the same thing. I have one log term on both sides. So I'm going to do 10 minus 4x equals 10 minus 3x. Subtract 10 over. Get negative 4x equals negative 3x. Now, this is only true in one scenario, and that's going to be when x equals 0, but I'm going to just continue this. So negative 4x plus 3x is negative x, and this is 0. So just to verify, log 10 minus 4 times 0 is just 0. Equals log 10 minus 3 times 0 is 0. So we end up getting log 10 equals log 10. So, yes. All right, for this one, we're going to set the ln terms equal to each other. So, n squared plus 12 equals negative 9n minus 2. Do the same thing we did before. Move the 9n and the 2 over to the other side. You get n squared plus 9n plus 14. This factors into n plus 7 and n plus 2. Since 7 plus 2 is 9 and 7 times 2 is 14. So this gives me two solutions, negative 7 and negative 2. So we can double check this. So negative 7 squared is 49 plus 12. Negative 9 times negative 7 is 63 minus 2. So this becomes 49 plus 12, 61. And this is also 61. So negative 7 works. And then I could also just do a really quick check for this one. And we end up getting ln of 16 equals ln of 16. So another correct solution. All right, over here. So they want us to figure out whether this is going to be growth or decay. There's a few ways that we could go about doing this, but honestly, my recommendation is just to plug it into the calculator. Makes life significantly easier. So I'm just going to do that. When you type in 100 times e to the ln of 0.5 to the x divided by 1590. When you graph this, you're going to have to make sure that you go into Zoom Fit. And the graph, all right, so it's kind of a weird graph. It kind of zigzags a bit. I guess if anything, it's more growth than anything. Yeah, it kind of oscillates between different points. Yeah, I wouldn't worry too much about that. The thing is, typically E ends up being a growth equation anyway. So you could say growth because the E term is going to be growing. And since the exponent isn't negative, all right, we'll do a few more questions. So this is what I was referring to before about combining the ln and log terms. So here we have two ln terms on the left, but we can't do that. So we're going to combine them. Since they're being subtracted, that means the two parts are being divided using the quotient rule. So we end up getting x minus 3 over x minus 5 equals 5. Cross multiply, and we get x minus 3 equals 5x minus 25. Minus 5x. And we end up getting negative 4x equals negative 22. Divide both sides by negative 4. And we get 5.5. All right. And down here, same thing. We have two terms on the left, so we have to combine them using the quotient rule. Log base 9, x plus 6 divided by x equals log base 9 2. X plus 6 over x equals 2. Cross multiply. X plus 6 equals 2x. Subtract the x over. And we end up getting x equals 6. And we could check that out. We can make sure this makes sense because it ends up boiling down to log base 9 of 12 minus log base 9 of 6 equals 2. All right, and here's the last question. So they want us to use the intersect function to determine which values of x will this work. So there's a few ways you can go about doing this. So you go in your calculator, you go absolute value of x squared minus 9, and then outside that you would write minus negative 3. And then the other equation will be log base 3 of x. Go to calculator's going a little slow. So you should end up with an equation or with a graph that looks something like this. Comes in, little semicircle, and then comes back out, almost like a cool W. And then that's one of the graphs, and then you get another one. The log term doesn't really appear too well on here. So from there, you go to intersect in the graphing calculator, find the two curves. And I get that x equals 2.29, round to the nearest 100. And this is something I could double check in a variety of different ways. But yeah, that's pretty much it for this. So a lot of this work is very similar to what we did with the exponents, except now we're just kind of combining the log terms and then doing what we did. All right, if you have any questions, feel free to let me know. Otherwise, see you later. Have a great day.